Welcome to A&M Education, College of Creativity and Technology. In this session, we will discuss about the topic Introduction to Binary Numbers. Introduction. There are 4 types of numbering system in digital computers. First one, decimal number system. This referred as base 10 and consists 10 digits, that is from 0 to 9. In this table, the column decimal represents decimal numbering system, which is also base 10. It contains the values 0 to 9. The later onwards, the 10 is the combination of 1 and 0. Second one, binary number system. This is referred as base 2 and contains 2 digits. They are 0 and 1. In this table, we can see that the binary numbering system, which contains base 2, has only 2 values, either 0 or 1. Third one, octal number system. This is known as base 8. It contains 8 digits. They are from 0 to 7. In this table, the column octal represents octal numbering system, which starts from 0 and ends with 7. When it comes to the higher position, like the decimal 8, it is represented with the combination of 1 and 0. Fourth one, hexadecimal number system. This is known as base 16. It contains 16 digits and it starts from 0 to F. In this table, hexadecimal column contains hexadecimal numbering system. Here, we can see that the number starts from 0 and ends with F. From 0 to 9, it is referred same as your decimal number. But when it comes to the position of decimal 10, it is referred as A. Number representation. A number with a decimal point is represented by a series of coefficients, that is A3, A2, A1, A0 dot A minus 1, A minus 2, A minus 3. Here, A3, A2, A1, A0 are the integer parts and A minus 1, A minus 2, A minus 3 represents fractional parts. A number expressed in base R system has coefficients multiplied by powers of R, that is an into r to the power n plus an minus 1 into r to the power n minus 1 plus up to a1 into r to the power 1 plus a0 into r to the power 0 plus a minus 1 into r to the power minus 1 up to plus a minus m into r to the power minus m. Here, an represents the coefficients, r represents base, and the power represents the position of the digits. Example, 4021.2 to the base 10. It is represented as 4 into 10 to the power 3 plus 0 into 10 to the power 2 plus 2 into 10 to the power 1 plus 1 into 10 to the power 0 plus 2 into 10 to the power minus 1, where 4 is nothing but the coefficient, 10 is nothing but the base value, and the power represents the position. First consider the integer part, that is 4, 0, 2, 1. 1 is at the position 0. 2 is at the position 1. 0 in 2. 4 in 3. Consider fractional part, that is 0.2, where 2 is positioned as minus 1. Example 2. 101.11 to the base 2. It is represented as 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0 plus 1 into 2 to the power minus 1 plus 1 into 2 to the power minus 2. Here, 2 is the base value and the power represents the position of the digit. Consider integer part, that is 101. The 1, it is in the position of 0. 0, it is in the position of 1, and 1, it is in the position of 2. Consider the fractional part, that is 0.11. Here, 1 represents position minus 1. This one represents the position minus 2. Number base conversion. First one, any base r to decimal conversion. A base r number can be converted to decimal by forming the sum of powers of base r of the coefficients. Example, binary to decimal conversion. 101 to the base 2. It is equals to 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0, where 1, 0, 1 represent the coefficients. 2 represents the base and the powers represents the position of each coefficients, which is equals to 1 into 4 plus 0 into 2 plus 1 into 1. Since any number with the power 0 is equals to 1, which is equals to 4 plus 0 plus 1 equals 5 to the base 10. Example for octal to decimal conversion. 630.4 to the base 8 equals to 6 into 8 to the power 2 plus 3 into 8 to the power 1 plus 0 into 8 to the power 0 plus 4 into 8 to the power minus 1. Here, 8 represents the base value. The digits 6, 3, 0, 4 represents the coefficients, and the power represents the position of the coefficients. That is, 4 represents minus 1. 0 represents 0th position. 3 represents the first position. 6 represents second position, which is equals to 6 into 64 plus 3 into 8 plus 0 into 1 plus 4 into 1 by 8, which is equals to 408.5 to the base 10, which is the answer. Second one, decimal to any other base or conversion. When we are converting decimal number to any other base system, we need to separate the integer part and fractional part. In integer part, we are using division method, and in fractional part, we are using the multiplication method. Example, 41.6875. We are converting this into binary. Consider integer part, that is 41, and it is divided with the base 2, because we are converting decimal 41.6875 into the binary. So, we need to divide the value 41 by 2. We get 20 and 1 as a remainder. We must divide the value up to 0. That is, 2 tens are 20, remainder 0. Again divided by 2, we get 5 and 0 as a remainder. Again divided by 2, we get 2 and 1 as a remainder. Divide 2 by 2, we get 1, the remainder 0. Again 1 is divided by 2, we get 0 and remainder 1. Now consider the value from bottom to up. We get 41 to the base 10, which is equals to 101001 to the base 2, which is in binary form. Let's consider the fractional part, that is 0.6875 into 2. When it comes to the fractional part, we are using multiplication method. Here, whatever the fraction is there, we have to multiply with the base. That is, 0.6875 into 2 is equal to 1 1.3750. Here, separate the integer part and consider it as a coefficient, that is, a minus 1 is equal to 1. Then, 0.3750 into 2, which is equals to 0.7500. Here, there is no integer part. Therefore, the coefficient a minus 2 is equals to 0. Again, take fractional part, that is 0.7500 into 2, which is equals to 1.5000. Since there is an integer part, consider it as a coefficient, that is a minus 3 is equal to 1. Now, 0.500 into 2 is equal to 1.0000. Here, coefficient a minus 4 is equal to 1. But there is no fractional part. Therefore, 0.6875 to the base 10, which is equals to 0.1011 to the base 2 when it is converted into binary form. Now, the answer will be the 41.6875 to the base 10 when it is converted into binary, we get 101,001.1011 to the base 2 as a final answer. Octal to binary conversion. Here, each octal digit is converted into 3-digit binary equivalent. That is, example 73.12 to the base 8, which is equals to 111,001.001010 to the base 2, where 111 represents 7, 011 represents 3, 001 represents 1 and 010 represents 2. Binary to octal conversion. The conversion from binary to octal is easily accomplished by partitioning the binary number into groups of 3 digits each, starting from the binary point and processing to the left and to the right. The corresponding octal digit is then assigned to each group. That is, example 101,011.1111 to the base 2. When it is converted into octal, we get 53.74 to the base 8. That is, 011 is equals to 3, 101 which is equals to 5 and 111 which is equals to 7 and 100 which is equals to 4. Suppose there is no digits, then we must add zeros to complete the group. Hexadecimal to binary conversion. Each hexadecimal digit is converted to its 4-digit binary equivalent. That is 16.d to the base 16. When it is converted into binary, we get 0001 0110 dot 1101 to the base 2, where 001 which is equals to 1, 0110 which is equals to 6 and 1101 which is equals to D. Binary to hexadecimal conversion. The conversion from binary to hexadecimal is easily accomplished by partitioning the binary number into groups of 4 digits each, starting from the binary point and proceeding to the left and to the right. The corresponding hexadecimal digit is then assigned to each group. Example 10110110 dot 1111001 to the base 2. When it is converted to hexadecimal number, we get B6.F2 to the base 16, where 0110 which is equals to 6 and 1011 which is equals to B and 1111 which is equals to F and 0010 which is equals to 2 in hexadecimal numbering system. Addition of two binary numbers. Example 101 plus 100. We get 1001. That is 1 plus 0 is equal to 1. 0 plus 0 is equal to 0. And 1 plus 1 which is equal to 10. In decimal, 1 plus 1 is equal to 2. We have to convert this 2 into the binary digit. Then we get 10. Therefore, 1 plus 1 is equal to 10. In binary system. But 1 plus 1 is equal to 2. It is in base 10, or we can say decimal number. Subtraction of two binary numbers. Example 110 minus 11. We get 011. Here 0 minus 1 is not possible. Therefore, we are borrowing 1 from the previous digit. That is 10 minus 1, we will get 1. Because in binary, 10 defines the decimal 2. 2 minus 1 which is equals to 1.